Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a second, that you have this ability to peer all the way back in time, like right to the very edge of the observable universe.
Which is a mind-bending concept on its own, honestly.
Oh, absolutely.
But
we're talking about looking at a time that's less than 550 million years after the Big Bang. And based on, well, basically everything astrophysicists have mathematically modeled for decades, if you look back that far to a redshift of roughly 10 or 12, you have a very specific expectation of what you're going to see.
right, you have a very established baseline.
Yeah. You're expecting to find these dark, faint, heavily obscured, dusty smudges of nascent galaxies. You're looking for these tiny structures just barely starting to pull themselves together out of the primordial gas.
Yeah, the expectation was essentially one of extreme optical dimness because, you're looking for the absolute earliest structures in the cosmos. So the assumption is that they are shrouded.
Like completely hidden.
Exactly. Hidden behind thick, undisturbed veils of this pristine cosmic material. It was supposed to be this very quiet, almost murky picture of the early universe, where the light of the first stars is just heavily suffocated by their surrounding environment.
So keeping that expectation in mind, put yourself in the shoes of the astronomical community when the James Webb Space Telescope finally opened its golden mirrors, calibrated the near-infrared camera, and actually looked at that exact epoch.
The collective shock was, it was palpable.
Because instead of those faint, dusty smudges, JWST found an early universe that was absolutely ablaze. It was just filled with galaxies shining with this unexpectedly intense, brilliant, unfiltered ultraviolet light.
It was a profound contradiction to all the established models of galactic evolution. And the brightness wasn't just some slight calibration error or minor anomaly, right? These objects were orders of magnitude brighter and the rest-free ultraviolet than the prevailing theories of galaxy formation could account for.
Orders of magnitude.
Yeah, it completely upended our understanding of what the cosmic dawn actually looked like.
To put the scale of this shock into perspective for you, imagine you're an explorer who uncovers a hidden door in an ancient ruin. And based on all the historical texts, you expect to open it and find, like, a dimly lit, smoky 1920s speakeasy.
Shadowy figures, heavy atmosphere.
Right. Thick cigar smoke blocking the dim incandescent bulbs, maybe a single piano playing quietly in the corner. But you swing the door open, and you are instantly blasted by a modern stadium rock concert.
Blinding lasers, pyrotechnics.
Yes. The atmosphere is totally clear of smoke, and the amplifiers are turned up to 11. That is the level of absolute whiplash we are dealing with here. And that brings us to the core mystery we are unpacking today. We're looking at a high-stakes astrophysical anomaly. How is the early universe so impossibly bright?
And the most fascinating part is that the central thesis, the actual physical mechanism that solves this puzzle, it doesn't lie in the stars themselves.
It doesn't.
Yeah.
And that forces us to look away from the light sources and actually examine the medium the light travels through. It lies in something that sounds, kind of mundane on the surface, but it operates on deeply complex physical principles. Ancient cosmic dust.
Right.
But to understand why this brightness was such a massive shock, we first really have to understand the mechanics of why these early galaxies were supposed to be dim. So let's unpack the anatomy of a cosmic shroud. Why do our baseline models dictate that young, star-forming galaxies should appear dark to an outside observer?
Well, it basically comes down to a fundamental mechanism in astrophysics known as attenuation. When we talk about a young galaxy, we're talking about a region experiencing a violent, furious rate of star formation. These localized areas are giant molecular clouds, often called stellar nurseries.
Okay, so stellar nursery.
Yeah. Now, when a new star ignites, especially the massive, really hot O-type and B-type stars that dominate the light profile of these young galaxies, they pump out an enormous flux of high-energy ultraviolet radiation.
So the stars themselves are undeniably bright. The photon production is definitely happening.
Oh, the raw photon production is immense. But in the standard local universe model of a young galaxy, those stellar nurseries are just completely choked with cosmic dust.
Like this speakeasy smoke.
Exactly. This dust is mixed right into the gas clouds where the stars are born. And this dust acts like a highly efficient optical blanket. So as the ultraviolet photons try to travel outward from the stellar photosphere and escape into the wider universe, they collide with these microscopic dust grains.
And what happens to the light then?
The dust absorbs the high-energy ultraviolet radiation, heats up, and then re-emits that energy as lower-energy, longer wavelength infrared light. Furthermore, the dust physically scatters the remaining UV light in random directions, deflecting it away from our line of sight. So this combined process of absorption and scattering, that is attenuation.
So from the perspective of an outside observer like JWST sitting out at Lagrange point 2, that galaxy appears incredibly dim in the ultraviolet spectrum because the internal dust blanket has essentially swallowed or deflected all that high-energy light before it could escape the galaxy's gravitational well.
Precisely. The standard local model operates on a proportional assumption. Lots of massive young stars means lots of heavy elements being processed, which equals a thick, efficient dust blanket, which equals a severely dimmed redder galaxy.
But JWST looks out, detects the distinct signatures of massive young star populations, but sees them blazing bright in the UV.
Yeah. The blanket is fundamentally failing to attenuate the light.
The blanket is missing, or the physics of the blanket are broken. That was the immediate crisis in cosmology. And whenever there's a sudden glaring contradiction between observation and theory, the community scrambles to line up alternative suspects.
Right, because you need to explain this missing attenuation, and you need to do it without breaking the laws of physics.
Exactly. So let's dig into the initial lineup of suspects, because we really have to understand why the obvious answers were mathematically wrong before we get to the real answer.
The initial reaction is always to look for a loophole in the existing frameworks before you go inventing new ones.
Right. So suspect number one was the idea that maybe the dust is there, behaving normally, but these galaxies are just experiencing insanely violent, sustained bursts of star formation, the superstarburst theory. Like, the idea that they're just overwhelmingly bright.
Yes, the hypothesis was that the sheer volume of ultraviolet photon production was so astronomically high that it simply saturated the dust's capacity to absorb it, just overpowering the blanket.
Pushing right through it.
Exactly. But that theory falls apart the moment you apply rigorous fluid dynamics and look at the Eddington limit.
Okay, let's define the Eddington limit for the listener, because that's the absolute hard ceiling for this theory, right?
It is. The Eddington limit is basically the natural balance point between gravity pulling matter inward and radiation pressure pushing it outward.
Radiation pressure. So, light pushing on things.
Yes. Photons carry momentum. If you pack too many massive, ultra-bright stars into a confined, giant molecular cloud, the physical outward pressure of their combined light becomes stronger than the gravitational binding energy of the gas cloud itself.
The light is literally so intense, it acts as a physical force that pushes the gas away.
Exactly. And if the star formation rate is as absurdly high as the superstarburst theory required to overpower the dust, that intense radiation pressure would physically blow the stellar nursery apart from the inside out.
Wow.
The galaxy would unbind its own star-forming gas, and that would immediately shut down any further star formation. So mathematically, a sustained super starburst of that magnitude is self-terminating. It's just physically impossible for them to be that bright for the durations we're actually observing.
Okay, so super starbursts are crossed off the list. The math just doesn't allow it. Suspect number two is a bit more nuanced. It was the idea of a skewed stellar population, specifically a wildly different initial mass function, or IMF.
Right, the initial mass function. This is the empirical rule that dictates the ratio of heavy, massive stars to small, low-mass stars when a gas cloud collapses.
Because they don't all form the same size?
No, not at all. In our Milky Way, for every massive, brilliant blue star born, you get hundreds of tiny, dim red dwarfs. It's a very bottom-heavy distribution.
But the theory here is that maybe the early universe was top-heavy. Maybe it almost exclusively formed massive, ultra-bright stars.
And the logic makes sense initially. A pristine, metal-poor gas cloud in the early universe cools less efficiently, which leads to larger fragmentation masses, meaning bigger stars. A top-heavy IMF would certainly produce more ultraviolet light per unit of gas mass.
Well, there's a catch.
A big catch. While it helps close the gap slightly, it still couldn't account for the systemic universe-wide lack of attenuation JWST was seeing. Furthermore, massive stars die quickly, and they eject massive amounts of dust-forming heavy elements when they do.
So they would make a ton of dust really fast.
Exactly. A top-heavy IMF would rapidly pollute the galaxy, creating an even thicker dust blanket very quickly, which completely contradicts the sustained bright UV observations.
So a top-heavy stellar population ultimately chokes itself out with its own dust. Okay, suspect number 3 was to look away from stars entirely. Hidden black holes, active galactic nuclei, or AGNs.
AGNs are incredibly efficient engines. When a supermassive black hole at the center of a galaxy actively accretes surrounding gas, that gas forms a wildly energetic accretion disk.
Just swirling around the event horizon.
Right. The friction and gravitational compression heat that disk to millions of degrees, causing it to shine brilliantly in the ultraviolet. And it can often outshine the entire host galaxy.
So the thought was, maybe we aren't looking at starlight at all. Maybe every single one of these early bright spots is just a feeding black hole masking itself as a galaxy.
It was a very compelling idea. But we don't just look at pictures, we take spectra. We take the incoming light and split it into its component wavelengths.
Like a prism.
Exactly. And an AGN accretion disk produces a very distinct chemical fingerprint. Specifically, extremely broad emission lines from high-velocity gas swirling near the event horizon, and highly ionized elements that require extreme radiation fields to exist, like ionized helium or carbon-5.
And when JWST's near-infrared spectrograph actually look for those specific fingerprints.
They largely weren't there, not in the general population of these bright galaxies. The spectra didn't match the violent high-energy physics of an accretion disk. They clearly displayed the narrower, lower ionization signatures of stellar photospheres.
So the light was undeniably coming from stars.
It was definitely starlight.
Which brings us to the final and most fiercely debated, discarded theory. The leaf blower theory, technically known as violent stellar feedback or momentum-driven galactic winds. I want to spend some time on this because it really dominated the discourse, and its failure is what leads us to the actual answer.
Yeah, it's a very intuitive model, honestly. The stellar feedback theory hinges on the fact that massive young stars are chaotic, violent neighbors. They emit ferocious stellar wind streams of charged particles flying off their surfaces, and, crucially, they end their short lives in supernova explosions.
And the theory proposes that if you pack enough of these massive stars into a young galaxy, their combined stellar winds and overlapping supernova shockwaves merge together to create a macro-scale event, like a literal galactic-scale hurricane sweeping outward from the galactic core.
Exactly, a mechanical clearing of the interstellar medium. The hypothesis was that this combined kinetic energy simply blasted the dust entirely out of the galaxy's gravitational well,
Just blowing the smoke right out of the room.
ejecting it into the intergalactic medium and leaving the stellar populations completely exposed, resulting in the blazing UV light we see.
I totally get the appeal of the idea. The stars build the blanket, and then the stars immediately blow the blanket away. But I really have to push back on the fluid dynamics of this, because I think the whole leaf blower analogy reveals a massive logical flaw when you apply it to a multi-phase interstellar medium.
Oh, absolutely.
Like if you have a sandbox, right, and it's full of heavy sand, which represents the dense, cold molecular gas where stars form, and there's a layer of fine light dust mixed all into it. If you take an industrial, high-powered leaf blower and point it at the sandbox to clear away the dust, you aren't just selectively removing the dust.
No, you're not, because they are dynamically coupled.
Right. The kinetic force required to eject all those microscopic dust particles against the gravitational pull of an entire galaxy would absolutely obliterate the cold hydrogen gas clouds as well. You would blow away all the sand. And galaxies explicitly need that cold, dense molecular gas to continue forming stars. If a galactic wind is powerful enough to clear out the dust blanket entirely, wouldn't it also clear out the star-forming fuel, effectively killing the galaxy?
That is precisely the hydrodynamical contradiction that dismantled the stellar feedback theory. Dust and gas are not separate entities floating side by side. They are intimately mixed. The dust is kinetically coupled to the gas.
So they move together.
Exactly. If a shockwave sweeps the dust away, it sweeps the gas away. And the question you just asked, how could a galaxy blow away its dust without blowing away its fuel, is what astronomers specifically set out to test.
And to test it, they couldn't just use JWST. They needed to look for the cold gas, the sand, in the sandbox. And this is where we find the smoking gun. Astronomers paired JWST's data with observations from a completely different type of observatory here on Earth, the Atacama Large Millimeter-Submillimeter Array, or LMA.
LMA is an incredible facility.
And by combining these two wildly different views, they isolated a specific classification of galaxies that broke the leaf blower theory permanently. They identified
GELDAs, galaxies with extremely low dust attenuation.
Let's break down exactly how these two observatories operate together, because it's critical to understanding the paradox they uncovered. JWST is operating in space, looking near infrared light. LMA is down in the Chilean desert, looking at millimeter wavelengths. How do they work together to look at the exact same object?
It's all about complementary spectroscopy. So JWST is designed to capture the light emitted directly by stars. But because these galaxies are so far away, say a redshift of 10, the expansion of the universe has stretched their original ultraviolet light all the way down into the infrared spectrum by the time it reaches us.
The light gets physically stretched to over 13 billion years.
Right. And JWST captures that redshifted starlight and confirms definitively that the ultraviolet light is escaping these GELDAs unimpeded. To JWST, the dust blanket is functionally non-existent.
It sees the blazing stars, but LMA isn't looking for stars at all.
No. LMA is an interferometer specifically tuned to detect the thermal continuum of cold dust and, more importantly, the specific rotational transition lines of molecules in cold gas. Specifically, it looks for carbon monoxide, or CO.
Wait, why carbon monoxide if the galaxy is mostly hydrogen?
It's a great question. Because cold molecular hydrogen, $22, is a symmetric molecule, and it lacks a dipole moment, meaning it's practically invisible at the frigid temperatures of deep space. It just doesn't emit radiation easily.
Oh, okay.
But carbon monoxide is highly asymmetric. As CO molecules tumble and rotate in these cold gas clouds, they drop down quantum energy levels and emit very specific bright photons at millimeter wavelengths. ALMA detects these CO emissions and uses them as a direct, reliable mathematical tracer to calculate the total mass of the invisible cold hydrogen gas hiding in the galaxy.
Okay, so JWST measures the starlight escaping, and LMA measures the exact volume of the cold, star-forming gas left in the tank.
Exactly. And when astronomers pointed LMA at these exact same GELDAs, the ones that JWST insisted had zero dust attenuation, they found an impossible contradiction.
The sandbox was still completely full of sand.
Full is an understatement. The measurements were staggering. These GELDAs, which are totally transparent to ultraviolet light, possess massive, undisturbed reservoirs of cold gas.
What kind of volume are we talking about here? Like, how gas-rich are they?
The metric they use is the gas mass fraction. Basically, the ratio of the mass of the unformed gas to the total baryonic mass of the galaxy. In some of these GELDAs, the gas fractions exceed 90%.
Wait, let me make sure I'm understanding that. 90% of the entire normal matter mass of the galaxy is just raw, unformed gas. Only 10% has actually condensed into stars.
Yes. They are incredibly inefficient at forming stars at this stage. They are essentially these vast, swirling oceans of raw fuel barely tapped into.
Okay, if we synthesize these two distinct data points, the logic is inescapable. The leaf blower theory says the violent stellar winds blew the dust away, leaving the galaxy bright. But basic fluid dynamics says if a wind was powerful enough to blast the dust into intergalactic space, it would have violently evacuated that cold gas reservoir too.
Yes.
You cannot have a macroscopic hurricane strong enough to clear all the dust, but delicate enough to leave a 90% gas reservoir perfectly intact and undisturbed.
It is physically impossible. You cannot decouple the dust from the gas in a kinetic blowout of that magnitude. If the gas is still there, resting quietly in massive quantities, then the mechanical blowout never happened.
Which leaves only one terrifyingly weird conclusion. Because the massive gas reservoir is definitively still sitting there. The dust must still be there too. The blanket hasn't been blown away. The dust is still physically present inside the galaxy.
The dust is absolutely there. It is mixed into the gas, just as we expect, but it is fundamentally failing to act like normal dust. It has somehow become, for all intents and purposes, optically invisible to the ultraviolet light produced by the stars.
Invisible dust.
Yeah. It is no longer absorbing or scattering the short wavelengths. It is just letting them pass right through.
An invisible blanket.
Yeah.
Okay, this is where the mystery pivots entirely. We move from where did the dust go to what the hell is wrong with the microscopic physics of this early universe dust?
How is that?
Because if the dust is definitively present but behaving invisibly, we have to look at how it was manufactured. We have to compare the dust floating around our modern Milky Way with the dust that existed 500 million years after the Big Bang. We have to examine the cosmic factories that build dust grains.
This is a vital distinction, and it's something often glossed over. Dust is not a fundamental particle like a proton or an electron. Dust is a complex, macroscopic, solid structure. It is a lattice of heavy elements, silicates, graphites, polycyclic aromatic hydrocarbons.
It has to be assembled.
Right, it has to be chemically manufactured. And the dominant manufacturing process in the universe today is fundamentally different from the only process available 13 billion years ago.
Let's ground this in the present day first. How does mature, light-blocking dust form in a modern galaxy like ours?
In a mature galaxy, the vast majority of interstellar dust is created through a slow, incredibly gradual process known as interstellar grain growth, or gas phase accretion. It happens deep inside the cold, dense molecular clouds.
How does it start?
The process starts with a tiny seed particle, usually a microscopic silicate core that was gently puffed out into space by the stellar wind of an aging, relatively low-mass star like an asymptotic giant branch, or AGB star.
A tiny little speck of soot floating in the void.
A very small speck. And as that speck drifts through the cold interstellar gas, it very slowly encounters heavier elements, astronomers call them metals, that are free-floating in the gas phase. Atoms of iron, carbon, silicon, oxygen. When an atom physically bumps into the seed, it sticks. It chemically bonds to the surface.
It's an accretion process, layer by layer.
Exactly. But you have to remember that even a dense molecular cloud in space is essentially a harder vacuum than anything we can produce on Earth. The physical distances between atoms are immense. So these collisions between the grain surface and a stray iron atom are incredibly infrequent.
Meaning it takes a very, very long time to build up a substantial dust particle layer by layer.
It takes hundreds of millions, often billions of years, of this slow, sweeping accretion for a galaxy to build up the massive, dense, highly efficient light-blocking dust grains that characterize the Milky Way today. The timeline is purely dictated by the slow collision rate.
And right there, you hit the glaring mathematical wall. That is the timeline crisis.
Yes, the math just doesn't work.
The universe today is 13.8 billion years old. Taking a billion years to slowly grow dust is perfectly fine in the modern era. But JWST is observing GELDAs at a redshift where the universe is less than 500 million years old.
Barely an infant in cosmic terms.
Right. The universe is a toddler. The entire lifespan of the cosmos at that point is shorter than the time required to build mature dust. Billions of years of gradual grain growth simply cannot exist in an environment that has only existed for a few 100 million years.
The mathematics of the accretion timeline completely forbid the modern method of dust production from being the dominant source, which means these early galaxies couldn't rely on AGB stars and slow accretion. They needed a rapid deployment dust factory, a mechanism that can forge solid grains almost instantly.
And what fits that bill?
Well, in the extreme environment of the early universe, there's really only one astrophysical mechanism violent and fast enough. The explosive deaths of massive stars, core collapse supernovae.
Supernovae is the primary dust factories of the early cosmos. If we use an analogy to separate these two eras, mature, modern dust formation is like rolling a snowball down a massive, miles-long, incredibly gentle hill. It slowly, gradually gathers mass layer by thin layer over a very long period of time until it's a giant boulder.
That's a great way to visualize it.
But early universe dust formation, relying entirely on supernovae, is like a massive bomb going off in a rock quarry. It is the instantaneous, violent, chaotic production of shattered material.
That analogy holds up surprisingly well to the physics, because a massive star, say, 20 or 30 times the mass of our sun, lives a very short, furious life. It acts as a localized nuclear forge, fusing lighter hydrogen and helium into heavier and heavier elements in its core, carbon, oxygen, silicon, all the way up to an iron core.
Just building up the periodic table inside itself.
Right, and this takes only a few million years, which is an eye blink in cosmic time. When it finally attempts to fuse iron, the core catastrophically collapses, and the subsequent rebound triggers a Type II supernova explosion.
And that explosion rips the star apart.
It violently ejects all those newly forged heavy elements outward at thousands of kilometers per second. And as that ultra-hot, rapidly expanding cloud of ejected material, the ejected begins to expand, it also begins to cool adiabatically.
Because it's spreading out so fast.
Exactly. And as the temperature drops below the condensation threshold of these heavy elements, they rapidly precipitate. They transition directly from a hot gas into solid molecular structures. They condense into solid dust grains right there in the expanding ejected cloud.
So the bomb goes off in the quarry, and the shockwave itself instantly condenses into a cloud of rock and dust.
It happens on a timescale of months to a few years after the explosion, not billions of years.
Okay, this perfectly solves the timeline crisis. The early galaxies are packed full of dust produced almost exclusively by supernovae. But here is the critical complication. A supernova explosion doesn't just create dust, deposit it gently into the galaxy, and fade away. The thermodynamic and fluid dynamic physics of the explosion itself violently alter the very dust it just created.
They absolutely do.
And this specific chaotic interaction is what leads directly to why this dust is effectively invisible to ultraviolet light.
This is where we dive into the deeply counterintuitive, highly destructive physics of a supernova remnant. It is not a single, simple outward blast. It's a multi-stage hydrodynamical event. The initial explosion sends a primary shock wave, the forward shock barreling outward into the surrounding interstellar medium at a significant fraction of the speed of light.
Right, the outward blast wave. That's the intuitive part. It pushes out.
But you have to consider what it's pushing into. The space around the star isn't entirely empty. It's filled with the ambient hydrogen gas of the galaxy. As the forward shock plows into this ambient gas, it sweeps it up, kind of like a snowplow.
Gathering mass as it goes.
Exactly. And as the mass of the swept-up gas begins to exceed the mass of the original stellar ejecta, the forward edge of the blast wave begins to rapidly decelerate.
So the front of the shock wave hits the friction of the surrounding gas and slams on the brakes.
Yes. It enters what we call the set-off Taylor phase. But remember, the material deeper inside the blast, closer to the origin point, is still rushing outward at incredible unimpeded speeds. So you have ultra-fast material slamming into the decelerating wall of the forward shock. This creates a massive, catastrophic buildup of kinetic pressure at that boundary layer.
And fluid dynamics dictates that this localized extreme pressure has to equalize. It has to go somewhere.
It must release, and it does this by launching a secondary shock wave. But because the forward path is blocked by the dense swept-up gas, this new pressure wave travels in the only direction available, inward. It bounces back. This is known as the reverse shock.
Wait, so the initial explosion hits the gas, creates a wall of pressure, and fires a hypersonic shock wave backwards into the very material that was just blasted outward.
Exactly. The reverse shock travels backwards in the co-moving frame right back into the expanding supernova ejecta. And what did we just establish is densely packed inside that newly expanding ejecta.
The freshly forged, rapidly condensed dust grains, the instant dust from the quarry bomb.
Yes. And this reverse shock is not a gentle breeze. It is a wave of immense thermal energy and kinetic violence. The gas behind the reverse shock is heated to millions of degrees. When this superheated, high-velocity plasma sweeps back through the newly formed dust cloud, it acts as a sieve of utter destruction. The intense heat and the physical collisions with high-speed ions essentially sandblast the dust grains.
They're eroding the dust they just made.
The technical term is thermal and kinetic sputtering. The high-energy plasma atoms collide with the solid dust grains and literally knock individual atoms off the grain lattice, one by one.
So the star creates a massive amount of dust and then immediately tries to vaporize it with a rebounding thermal shock wave.
It does vaporize a massive fraction of it. The reverse shock significantly reduces the total overall dust mass of the supernova remnant. But sputtering is ruthless in a highly specific, size-dependent way. The timescale for destroying a dust grain via sputtering is directly proportional to its radius.
Meaning smaller things die faster.
Exactly. The tiny microscopic dust grains, the ones less than about 0.01 micrometers in radius, simply do not have enough mass or surface area to survive the onslaught. They are completely shattered, vaporized back into the gas phase entirely. They do not survive the passage of the reverse shock.
Okay, the small grains are completely annihilated. But what about the larger ones?
The larger grains, those above 0.1 micrometers, take heavy damage, certainly. Their outer layers are eroded. But because they started out with significantly more volume, a substantial core of the grain survives the passage of the reverse shock.
So what emerges from a supernova remnant, after the explosion has faded, the reverse shock has dissipated, and the material finally mixes with the galaxy, is a heavily curated, heavily damaged population of dust. Almost all the small grains have been vaporized, and what remains is a population heavily dominated by unexpectedly large surviving grains.
That is the exact physical mechanism. The supernova effectively filters its own dust.
And here is the grand reveal. This is the key to the entire JWST puzzle. You have early galaxies filled exclusively with dust that has survived a reverse shockwave, meaning the dust is composed almost entirely of these large grains. And as it turns out, these surviving large grains are intrinsically optically transparent to the ultraviolet light produced by the young stars.
That is the optical secret that explains the geldas.
But I have to stop you here because I need to challenge this on an intuitive level.
Yeah.
Because in the macroscopic everyday world, bigger objects block more light. If I hold up a tiny grain of sand to a flashlight, a tiny bit of light gets blocked. If I hold up a massive brick, all the light gets blocked. How can astrophysics possibly dictate that bigger dust particles in space block less ultraviolet light? Why is a galaxy full of physically large dust grains effectively transparent?
It is a brilliant question, and it highlights exactly why human intuition fails when dealing with the physics of light scattering. To understand this, we have to step away from the idea of blocking like a brick wall and look at the quantum electrodynamics of light interacting with matter, specifically Mie scattering theory.
Okay, Mie scattering, MIE, right?
Yes. When we are dealing with particles on the microscopic scale, which even these large cosmic dust grains are, the way they interact with a photon depends almost entirely on the mathematical relationship between the physical radius of the particle and the exact wavelength of the light hitting it.
Okay, so it's a ratio. Size of the grain versus the size of the wave.
Yes. It's called the size parameter. Now, small dust grains, the tiny ones that were completely vaporized by the reverse shock, are roughly the same physical size as the wavelength of ultraviolet light. When a particle's radius is comparable to the wavelength of the incident light, it hits a resonance peak. It is incredibly, overwhelmingly efficient at interacting with that light. It scatters the wave violently in all directions, and it absorbs the energy efficiently.
It's tuned perfectly to catch that specific wave, like how a perfectly sized antenna catches a specific radio frequency.
That is a perfect analogy. It is a resonance effect. This is very similar to Rayleigh scattering, which governs why our sky is blue. The small nitrogen and oxygen molecules in our atmosphere are the perfect mathematical size to aggressively scatter short wavelength blue light across the sky while letting longer red wavelengths pass through.
So small dust grains are perfectly tuned antennas meant to catch and scatter short, high-energy ultraviolet light.
Exactly. If you have a galaxy full of small grains, no UV light escapes. But large grains, the battered survivors of the supernova reverse shock, are physically much larger than the wavelength of UV light. Because they are so much larger, that resonant efficiency completely drops off. They operate in a different regime of optical physics, closer to the geometric limit.
The wavelength is too small for the antenna to catch it efficiently.
Precisely. Because of this mismatch in scale, the large grains are highly inefficient at scattering or absorbing those specific short UV wavelengths. The extinction curve flattens out. The UV light essentially just diffracts slightly around the edges of the grain or passes through the wider physical gaps in the dust population without being heavily absorbed or deflected.
Wow.
Yeah, counterintuitively, because the grains are so aggressively large compared to the light wave, they lose their resonant ability to act as a solid optical blanket. Their attenuation efficiency per unit mass drops off a cliff. To a UV photon, the large grain is a poorly tuned obstacle and the photon simply bypasses it.
That is astonishing. The very violence of the supernova explosion, the reverse shock specifically destroying the small antennas, ensures that the only dust left over is mathematically guaranteed to be poorly tuned to block the light of the young stars. It's like the explosion creates a custom-built window out of its own blast radius.
It's an incredibly elegant feedback loop, yes.
But knowing how a few particles of supernova dust act in a laboratory vacuum or a computer simulation is one thing. Proving that this microphysics mechanism scales up to explain the macro behavior of entire massive galaxies requires a massive conceptual leap. You need a complex radiative transfer model to prove it actually works on a galactic scale.
And that necessity brings us to the breakthrough research that really cemented this entire theory. We have to discuss the analytical framework developed by a team led by Di Bergarella at the Laboratoire d'Astrophysique de Marseille.
The Marseille framework. Because Bergarella and his team didn't just guess that large grains would solve the JWST problem, they built a rigorous multi-parameter mathematical model to test if this specific type of dust could physically reproduce the exact light curves and attenuation properties JWST was sending back.
Right, it had to be proven mathematically.
And to do this, they combined 3 distinct astrophysical ingredients into their simulation. Let's break these down. Ingredient number 1 is straightforward based on our discussion.
Yes, the first ingredient is the foundational physics we just covered. The known optical properties of supernova-produced dust. They took the mathematically derived opacity curves of large-grain, reverse shock-surviving dust and inputted them into their models. They essentially programmed the simulation to recognize the dust in this specific galaxy does not scatter UV light efficiently.
Okay, ingredient number 2 involves how that opacity mathematically scales with a galaxy's overall metal content.
Right. They tied the dust properties to the galaxy's metallicity. And we should clarify for the listener, astronomers use a very quirky historical periodic table. To an astrophysicist, the universe is made of hydrogen and helium. Literally every other element on the periodic table, carbon, oxygen, nitrogen, iron, gold, is collectively lumped together and called a metal.
So a high metallicity galaxy has a large abundance of heavy elements, like our Milky Way, and a low metallicity galaxy is mostly just pristine, primordial hydrogen and helium.
Exactly. The Marseille framework had to mathematically account for how the dust interacts with its surrounding environment based on the sheer volume of metals available in the gas phase. Because even if individual large dust grains are highly transparent, if you have an incredibly high density of heavy elements, the overall chemical composition of the gas phase will eventually start affecting the total attenuation of the galaxy.
So they had to scale the optical transparency to the chemical evolution of the host galaxy.
Right, it's a dynamic scaling.
Okay, they have the optical physics of the large grains, and they have the chemical scaling of metallicity. But ingredient number 3 is the one I find the most spatially fascinating. It's the physical arrangement of the stars and the dust clouds within the three-dimensional space of the galaxy itself. The geometric structure.
This is a huge factor.
The research focuses heavily on what they define as a porous geometry, or a multi-phase interstellar medium. What exactly does physical arrangement mean in the context of galaxy-wide attenuation?
To understand this, you have to think about how astronomers traditionally and simplistically modeled dust in a galaxy before we had the computing power we do now. For a long time, the easiest way to mathematically model attenuation was to assume the dust formed a uniform, homogeneous screen. Imagine a flat, perfectly smooth, solid sheet of tinted glass placed perfectly between the emitting star and the observing telescope.
A solid uniform blackout curtain. Every photon has to push through the exact same thickness of dust.
Right, a homogeneous screen geometry. But the Marseille framework incorporated advanced hydrodynamical reality. They recognized that supernova dust does not gently settle into a uniform, smooth sheet. The chaotic, turbulent, highly explosive nature of supernovae means the interstellar medium is violently churning.
It's a mess in there.
It is. The dust is distributed in a highly fractured multi-phase state. It clumps heavily together in incredibly dense, localized nodes, but it leaves vast, empty, swept-out voids in the spaces between those nodes. This is the porous geometry.
So if standard models treat dust like a uniform blackout curtain, supernova dust arranged in a porous geometry is more like a complex three-dimensional labyrinth of fractal tunnels. Or, to use a simpler visual, a giant celestial sponge.
A sponge or a highly fractured lattice are excellent visuals. You have dense structural chunks of dust, the solid parts of the sponge, but you also have massive intersecting empty pathways winding through it.
And because the dust is clumped into this porous fractal geometry, the ultraviolet photons from the stars don't have to try and push their way through a solid, uniform wall of dust.
Precisely. Light obeys the laws of radiative transfer. The photons travel along the paths of least resistance. The vast majority of the UV light simply scatters off the dense clumps and channels its way through the empty macropores, leaking out of the galaxy through the physical gaps in the dust structure.
The light navigates the labyrinth. So when Bergerella's team combined these 3 specific ingredients, the dust is made of fundamentally large grains that are intrinsically inefficient at scattering UV, the overall metallicity of the system is low, and the dust that does exist is clumped into a porous, hole-filled structure.
The mathematical result is a galaxy that offers almost zero systemic resistance to the escape of ultraviolet photons. The escape fraction approaches the very levels JWST is observing.
The ultimate recipe for a blazing bright galaxy. And the most incredible part of the Marseille team's work isn't just the theory, it's the validation. When they took this highly specific 3-ingredient stardust model and ran it forward to simulate populations of early galaxies, the simulated light curves perfectly matched the actual, real-world photometric counts observed by JWST.
That is the absolute gold standard of theoretical astrophysics. It reproduced the exact observed anomaly without needing to invent a single line of exotic, unproven physics.
They didn't have to make anything up.
No, they didn't need to conjure up Eddington-violating superstar bursts. They didn't need hidden black holes that lacked spectral evidence. They just rigorously applied the complex fluid dynamics and optical physics of supernovae that we already know operate in the universe.
It's incredibly elegant. It solves the profound mystery of the early universe, using the natural, inevitable consequences of massive star death. But as with all great science, this elegant solution immediately opens up an entirely new, deeply profound question.
It always does.
Right. If early galaxies were naturally filled with this invisible, porous, large-grain supernova dust, why don't modern galaxies look like this? Why is the Milky Way currently choked with thick, highly efficient light-blocking dust if supernova dust is the natural byproduct of star formation?
That is the crucial evolutionary question. And the beauty of the Marseille stardust model is that it actually accounts for this. It doesn't just explain the anomaly. It reveals the exact moment the universe, for lack of a better term, grew up.
It models a transition.
It reveals a profound evolutionary tipping point. The framework doesn't just state that the early universe is one way and the modern universe is another. It successfully tracks the chemical evolution over time and maps out a specific transition regime. It shows the exact mathematical conditions under which a galaxy evolves from relying on rapid supernova dust factories to relying on the slow, mature, highly efficient grain growth process in the interstellar medium.
And the researchers identified a highly specific mathematical threshold for this transition, right? A critical tipping point in the galaxy's life cycle.
Yes. They identified a critical metallicity threshold, and it sits at roughly 1/10 of our sun's current metal content. Mathematically, its Z-crit is roughly 0.1 Z solar.
1/10 solar metallicity. Let's walk through the timeline of how a galaxy crosses that line.
Okay, so when a galaxy first forms from the primordial intergalactic medium, it is pristine. It is essentially 100% hydrogen and helium. Its metallicity is effectively zero, sitting far, far below that 1/10 threshold. In this early era, as we established, supernovae are the absolute only entities capable of producing dust fast enough.
Right, the early bomb in the quarry.
Exactly. So supernova dust physically dominates the interstellar medium. The grains are uniquely large, the geometry is chaotic and porous, and the optical attenuation is extremely low. This is the era of the bright, blazing, transparent early universe that shocked JWST.
But as millions of years tick by,
as time progresses, generation after generation of massive stars are born, live out their short lives, and die. And every single time one of those stars explodes in a supernova or puffs off its outer layers as an AGB star, it injects newly forged heavy elements, silicon, carbon, iron, into the interstellar gas.
the sandbox gets dirtier.
Yeah, the galaxy slowly gets more and more polluted with metals. The baseline chemical composition of the gas phase rises. And eventually, after hundreds of millions of years of this continuous stellar recycling, the overall metal content of the entire galaxy crosses that critical 1/10 solar threshold.
And what specifically happens at the microscopic level when the galaxy crosses that 1/10 line? Why is that the tipping point?
Because at that specific metallicity, a critical mass is reached in the gas phase. There are finally enough stray, heavy atoms floating around in the cold, dense molecular clouds that the slow, gradual process of interstellar grain growth suddenly becomes highly efficient.
Oh, there's finally enough material for the snowballs to grow.
Exactly. The probability of an iron atom colliding with a seed grain crosses a threshold. The slow accretion process physically outpaces the destructive power of supernovae.
The galactic factory basically switches production lines.
That's a great way to put it. The galaxy transitions chemically and optically. It shifts from being dominated by transparent, large-grain supernova dust to being completely dominated by the small, highly efficient, heavily accreted, opaque dust grains of the interstellar medium. The porous holes fill in, the dimming rises sharply, the optical blanket becomes thick and uniform, and the galaxy fundamentally darkens in the ultraviolet spectrum. It matures.
And what blows my mind about this specific threshold, this 1/10 transition line, is that it isn't just theoretical math born in a computer simulation. Astrophysicists have theorized about a critical metallicity transition for years based on observing tiny ancient dwarf galaxies lingering in our local neighborhood that happen to have low metallicity.
Right.
But JWST's observation of these geldas, these incredibly bright, gas-rich galaxies sitting deep in the cosmic past, represents the very first time humanity has watched this cosmic transition happening live.
It is observational cosmology operating at its absolute finest. Because of the finite speed of light, peering deep into space is identical to peering deep into the past. We refer to this as observing at high redshift, the cosmological stretching of the photon's wavelength that tells us exactly how far away and thus how far back in time an object is.
Right.
By explicitly observing populations of geldas at high redshifts, we are literally watching populations of galaxies cross that 1/10 solar threshold in real time. We are watching the exact epoch where the universe switched from its transparent, chaotic, bright youth to its dusty, opaque, hidden maturity.
That concept just gives you chills when you really think about the scale of it. We are watching the universe pull the blanket over its own head. But looking at these specific geldas, the ones that exist below that 1/10 threshold, the ones that are still highly pristine, it brings us to the absolute edge of astronomical history. Because analyzing the dust in these specific objects points directly to a theoretical class of objects that are considered the holy grail of modern astrophysics. We have to talk about population that are stars.
Population 3 stars. They are the white whales of stellar astrophysics.
Let's define them for the listener, because the astronomical naming convention is frustratingly backwards. We, meaning our sun, are population I, right?
Yes, the naming is entirely historical based on when they were classified, making it slightly counterintuitive chronologically. Our sun, and the vast majority of the stars forming in the spiral arms of the modern Milky Way, are population I stars. They are metal-rich, they contain a high percentage of heavy elements that were forged by previous generations and mixed into the gas they formed from.
Okay, so that's Pop 1.
The older, redder stars that live in the spherical halo of our galaxy or in globular clusters are population 2. They're older, significantly more metal-poor, but they still contain measurable trace amounts of heavy elements.
Which means population 3, chronologically, are the absolute oldest.
Population 3 stars represent the universe's very first stellar generation. They're the stars that ignited in the absolute, pristine darkness following the cosmic dark ages, shortly after the Big Bang. And what makes them totally unique from an astrophysical standpoint is their chemical composition.
What were they made of?
At the time they coalesced from the primordial halos, the universe contained absolutely nothing but hydrogen, helium, and a tiny, functionally negligible trace of cosmological lithium. There was 0 carbon, 0 oxygen, 0 iron.
0 metals. Pure, unpolluted, pristine gas.
And that extreme lack of metals fundamentally alters how a star forms. In modern star formation, heavy elements like carbon and oxygen act as critical coolants. They radiate heat away from a collapsing gas cloud via fine structure emission lines, allowing the cloud to fragment into smaller pieces, creating normal-sized stars like our sun.
But Pop 3 didn't have those coolants.
Right. Because population 3 gas clouds had 0 metals, they lacked this cooling mechanism. They could only cool via very inefficient molecular hydrogen transitions.
Meaning the cloud couldn't fragment easily.
Exactly. The minimum mass required for gravity to overcome thermal pressure and collapse the cloud was astronomically high. Theoretical models dictate that population 3 stars couldn't be small. They had to be incredibly massive. We are talking monstrous, hypergiant stars, routinely 100 to 300 times the mass of our sun.
300 times our sun.
Yeah. Because of this extreme mass, they would have burned incredibly hot, incredibly bright, and lived extremely short lives, perhaps only 1 million years, ending in uniquely titanic supernovae. Some likely ended in what we call pair instability supernovae, which literally obliterate the entire star, leaving no black hole behind, just a massive expanding cloud of freshly forged elements.
But the crucial, frustrating point to reiterate here is that despite all our advanced theoretical models, despite decades of searching the deep sky, a purely metal-free population 3rd star has never been directly observed by a telescope. Not once.
Never. They lived and died so furiously quickly and so early in the universe's history that catching an individual one in the act of shining is phenomenally difficult, perhaps impossible with current technology.
But this is where the Stardust framework connects the dots in such a beautiful, indirect way. Connect the elusive population that are stars back to the transparent dust we've been discussing for the last hour.
Think about the mechanics of the death of a massive population 3rd star. It explodes in a completely pristine environment. Its pair instability supernova is the very first event in cosmic history to inject heavy elements into the virgin intergalactic medium. And just like we discussed with standard supernovae, The fluid mechanics of that explosion, the outward blast wave hitting the dense primordial halo, the immense reverse shock rebounding inward, would have produced the exact large-grain, low-opacity reverse shock surviving dust that the Marseille framework requires.
The transparent dust.
Yes, the invisible stardust. The researchers realized a profound implication of their model. When they look at the most extremely metal-poor geldas in their observational sample, the galaxies furthest back in time, hovering right on the edge of the cosmic dark ages, the transparent, large-grain dust they are mathematically detecting might not just be from early population 2 stars.
It could be older.
It is highly probable that it might be the direct relics, the literal physical ashes of the population 3 stars themselves.
The ashes of the first giants. That is staggering to contemplate. But how would we even know for sure? From an observational standpoint, how do you prove that this specific cloud of transparent dust came from a first-generation population that are hypergiant, and not just a really old, massive population 2 star that exploded a few million years later?
That is the next great frontier of chemical archaeology. The researchers believe that the nucleosynthetic signatures of those first massive supernovae will be uniquely imprinted on the dust they left behind. A 200 solar mass population 3 star exploding via pair instability forges elements in fundamentally different ratios than a 20 solar mass population 2 star undergoing a standard core collapse.
The recipe of the bomb is different.
Exactly. The specific elemental ratios, for instance, a highly distinct odd-even effect in the elemental yields, or specific ratios of carbon to silicon or oxygen to iron, will be fundamentally distinct in the resulting dust lattice. And as our instruments and spectroscopic models become more refined, we might soon be able to detect those specific chemical fingerprints.
So we wouldn't see the star, but we would read its exact elemental signature in the dust.
Yes. In the subtle microscopic variations of the attenuation properties, the precise gas phase metallicity measurements, and the specific wavelength of mid-infrared light the dust emits when it's warmed by the ambient radiation field.
I just have to pause and marvel at this concept, because it perfectly encapsulates why astrophysics is so compelling. We are talking about trying to find the very first stars ever born in the universe. Entities that vanished entirely 13 billion years ago, leaving no core behind. And the way we are trying to find them isn't by looking for their light. It's by studying the invisible, shattered, physically eroded dust they left behind in their death throes. By mathematically analyzing the optical properties of this transparent cosmic mist, we are essentially reaching across space and time and touching the structural remains of the universe's first light. It's like reconstructing the exact physical dimensions of a ghost by studying the shape of the footprint it left in the sand.
It is cosmological archaeology at its most profound and challenging.
But as thrilling as it is to talk about finding the ashes of the first stars, and as beautifully and elegantly as the Marseille framework ties all this physics together into a neat bow, true scientific inquiry requires rigorous skepticism. We have to look at the path forward, and the specific caveats that Bergerella and the researchers themselves are actively putting out there.
Absolutely. Scientific humility is paramount, especially when dealing with the extreme environments of the early universe where we cannot directly test our fluid dynamics. The researchers are very careful not to overstate their conclusions as absolute law yet. The Stardust framework matches the observed population of bright galaxies incredibly convincingly. The radiative transfer math works, but the precise, exact microphysical properties of early universe supernova dust remain somewhat uncertain.
Meaning, we have great mathematical models for how Sedov-Taylor phases and reverse shocks work, but we've never actually stood inside an early universe supernova remnant to measure the dust grains with a cosmic ruler.
Precisely. We are extrapolating the reverse shock destruction efficiencies based on the best plasma physics available, but the early universe was a highly chaotic, dynamic place. The authors raise a very specific and important caveat regarding what they call galactic variance.
Galactic variance, what does that mean practically in this context?
It means that while the general systemic rule of supernovae produce large transparent grains seems mathematically solid, the specific grain size population emerging from those supernovae at high redshift might vary wildly from one individual galaxy to the next. The universe is not a monolithic factory line.
There are local variables.
Right. Depending on the exact initial mass of the specific stars exploding, the varying density of the pristine gas halos they are surrounded by, the ambient temperature of the local intergalactic medium, all of these localized factors could drastically alter the efficiency of the reverse shock.
Though the reverse shock might be weaker in one galaxy and stronger in another.
Exactly. One gelda might have dust that is 90% transparent because it had an incredibly dense dense surrounding medium that triggered a massive reverse shock, while another gelda right next to it, born under slightly different initial conditions in a less dense halo, might have a weaker reverse shock, resulting in dust that is only 70% transparent.
The universe is messy. There are error bars on the Swiss cheese. So how do we solve that remaining uncertainty? How do astrophysicists plan to map the messiness and reduce those error bars?
We need more high-resolution data, and we need it across multiple specific wavelengths to break the mathematical degeneracies in our current models. This is where the roadmap for the next decade of observational astronomy comes into focus. The astronomers highlight the critical, specific need for coordinated, simultaneous future observations.
Using JWST and LMA again.
Exactly. We need to push JWST further. Specifically, we need to use its MRI instrument, the mid-infrared instrument, to take deeply detailed spectroscopic measurements of the actual thermal emissions of the dust itself, not just the starlight slipping past it. We need to pinpoint the exact attenuation curves of individual galaxies.
We need to see exactly which specific wavelengths of light are slipping through the pores of the geometry and which are being caught.
Exactly. That gives us the exact size parameter of the grains. And alongside JWST, we need to push LA even harder. We need high-resolution radio interferometry to map the spatial distribution of the cold CO gas and the cold dust continuum with even greater precision. If we can pin down the exact dynamical mass of the gas alongside the exact optical properties of the dust on a galaxy-by-galaxy basis, we can move the stardust framework from a highly convincing, elegant theoretical model to an irrefutable, observed law of early cosmic evolution.
It is an incredible, highly specific roadmap for the next decade of astronomy. We are going to bring this journey back from the edge of the universe now. To summarize the sheer scale of the physics and the timeline we've unpacked today, we started with a telescope that opened its infrared eyes, expecting darkness, expecting to find the faint, muddy, obscured smudges of a dusty cosmic dawn. Instead, it found a blinding, brilliant, blazing epoch of unfiltered light.
A cosmic dawn that violently defied the standard models of attenuation and galaxy formation.
And to solve that massive contradiction, we had to discard the intuitive but flawed ideas of galactic leaf blowers, momentum-driven winds, and Eddington-violating superstarbursts. We had to stop looking at the light sources and look at the microscopic physics of the dust itself. We realized that the explosive, violent deaths of massive stars, the core collapse supernovae, don't just instantly create matter. Their complex fluid dynamics act as a reverse shock sieve, thermally sputtering and shattering the microscopic grains, leaving behind a heavily curated population of mathematically large dust.
Dust that organizes itself into a chaotic, porous, fractal geometry, allowing the ultraviolet light to scatter through the macroscopic channels.
It acts like a custom-built cosmic window rather than a solid, uniform wall, which finally elegantly explains how a galaxy could be packed full of cold molecular gas and star-making material, a completely full sandbox, but still shine with blinding, unattenuated brilliance.
It completely reframes our understanding of the mechanics of the early universe. It forces us to view destruction as an optical filter.
It really does. And as we wrap up, I want to leave you, the listener, with a final lingering thought to ponder on your own. Take a moment to think about the physical world around you right now. Think about the iron flowing through your blood, the calcium structure of your bones, the silicon microchips in the device you might be listening to this on. Every single one of those heavy elements, every atom heavier than helium, was forged in the nuclear heart of a massive star and violently ejected into the void by a supernova.
It is the rigorous, literal truth behind the famous "we are made of star stuff" concept. We are the accretion of stellar ash.
Exactly. The physical, opaque dust we sweep off our floors today, the solid rock of the Earth we stand on, is a direct, billions of years old evolutionary descendant of the slow gas phase accretion processes we discussed. But consider the profound poetry of this timeline, the very thermodynamic mechanism that eventually created the solid, opaque, heavy matter of our localized world, the planets, the continents, our own bodies. That exact process began in the early universe, not as a dark, heavy, suffocating blanket. It began as a transparent, shattered, aggressively eroded mist. It began as a porous, invisible window that deliberately allowed the very first light of the universe to escape its localized gravity well, to shine across the expanding cosmos, traveling to 13 billion years just to reach our telescope mirrors today. How does it feel to know that destruction, the immense violence of a reverse shockwave, and the resulting optical transparency were the necessary absolute mathematical prerequisites for creation, for solid form, and ultimately for us to even be able to observe the blazing beginnings of our own cosmic history?